is equilibrium of forces too. Here is a quick crash course to give you a thorough understanding before my main video surfaces. Enjoy.
Now, we've often described the physics of objects based on their mass, but when it comes to fluids, we mostly use a different quality. Density, represented in equations by the Greek letter ρ. You're probably familiar with density. It's mass divided by volume and measured in kilograms per meters cubed. If an object or a fluid is made of heavier atoms or molecules, or those particles are packed more closely together, then it's going to have a higher density. And there's another important quality of fluids, one that scuba divers and mountain climbers think about a lot. Pressure. In our last episode, we defined pressure as applied force divided by area. It's measured in units of newtons per meter squared, known as pascals. And fluids apply pressure in every direction. So right now, there's air putting pressure on you and me from every side. In fact, the average air pressure at sea level is 101,325 pascals. And if you jumped in a pool, the water would also exert pressure on you. But if you've ever tried diving to the bottom of a pool, you'll know that there's more pressure at the bottom than at the surface. Which is why at the bottom, your ears hurt and your head feels like it's about to implode. That's because the deeper you go, the more fluid there is above you, with its weight pressing down. There's an easy way to calculate the pressure of a fluid at a given depth. It's just the fluid's density times small g times the distance to the surface, represented by the letter h for height. And the change in pressure based on depth is equal to the fluid's density times small g times the change in distance to the surface. So let's say you're swimming in a pool that's 3 meters deep and you want to know how much more pressure you'll experience at the bottom of the pool versus how deep you are now, which is, let's assume, 1/4 of a meter. The density of the water is 1,000 kilograms per meters cubed, and the change in distance to the surface is 2.75 meters, which means that the pressure at the bottom of the pool is 27,000 pascals more than the pressure 1/4 of a meter down. The water in the pool could be one example of a confined fluid, because if you had a piston the size of the pool's surface and used it to push down on the water would have nowhere to go. And back in the mid-1600s, French physicist Blaise Pascal realized something about the way pressure worked in confined fluids. If you apply pressure to a confined fluid, the pressure in every part of the fluid increases by that amount. If you have water in a cup and you use a piston to apply 10,000 pascals of pressure to the surface of the water, then the pressure everywhere in the water increases by 10,000 pascals. Today, that concept is known as Pascal's principle, and it's the reason hydraulics are so useful. Say you have some water in a tube with pistons on either side. Pascal's principle tells you that if you use the piston on the left side to apply pressure to the water will exert the same pressure on the piston on the right side of the tube. And the pressure is equal to the force divided by the area. So say you have another tube that's more of a cone shape, with a piston on the left side that has an area of 1 meter squared and one on the right that has an area of 2 meters squared. Again, you apply 10,000 pascals of pressure to the piston on the left side, meaning 10,000 newtons of force. But the piston on the right side has double the area. So for the pressures to be equal, the water has to apply double the force to the piston as you apply to the water. And so you end up with 20,000 newtons of force on the right side piston. This is a huge deal. You're doubling the input force, but you didn't have to put in any extra effort. And the bigger the difference in area, the more extra force you get. To put it in maths terms, the ratio of the output force to the input force is equal to the ratio of the output area to the input area. Systems like hydraulic lifts take advantage of this by having big differences in area on either side of the fluid. So if you want to apply a lot of force to lift something heavy, for example, hydraulics are the way to go. Now, if you're going to be using pressure to do stuff, you're probably going to want to be able to measure that pressure, which is where manometers and barometers come in. A manometer is just a U-shaped tube with a fluid inside. Say you wanted to use one to measure the pressure of a bike tyre. You'd stick one side of the tube in the tyre, leaving the other side open to the atmosphere. If there's a difference in the pressure on each side of the manometer, whichever side has the higher pressure will push the fluid away from it, creating a difference in the height of the fluid on either side of the U. In this case, the inside of the bike tyre has a much higher pressure than the atmosphere, so the level of the fluid on the side of the U that's closer to the tyre will be lower. If you measured the difference in fluid height directly, you'd get what's known as gauge pressure, the difference between atmospheric pressure and the pressure inside the tyre. But the actual pressure of the tyre, the absolute pressure, is the atmospheric pressure plus the gauge pressure. So the pressure inside the tyre will be equal to the atmospheric pressure plus the density of the fluid inside the manometer times small g times the difference in the heights of the fluid. Barometers, on the other hand, use a long vertical tube that's closed on one end, usually filled with mercury and then stuck upside down in a bowl that's also full of mercury, with the closed end of the tube at the top. The pressure of the atmosphere pushes down on the mercury in the bowl, which keeps a certain amount of mercury in the tube. At standard atmospheric pressure, the mercury in the tube will be exactly 76 centimeters high. If the air pressure goes up, so does the level of mercury, and vice versa. So we have one more property to talk about when it comes to fluid at rest, and it's the one that supposedly made that guy run naked through the streets yelling Eureka! That guy was Archimedes, and he lived in Greece in the 3rd century BCE. Legend has it that he was asked to find a way to figure out if the king's crown was pure gold, and the best way to do that was calculate its density. Archimedes could measure the crown's mass easily enough, but he didn't know how to find its density. He was taking a bath one day when he realized that the volume of the water displaced by an object is equal to that object's volume. And since he already knew the crown's mass, that meant he'd be able to find its volume, and therefore its density, just by putting it in water. That's when he did the whole running through the streets naked thing. So Archimedes discovered that when you put something in a fluid, the fluid's volume increases by the amount of the object's volume. This tells us a lot about what makes objects float or sink. For example, say you have a tub of water and two balls of the same size, but of different densities. Say one is an American-style billiard ball and the other is a racquetball. We're going to gently place the balls in the middle of the tub, let go, and explain what happens to them. But first, let's talk about the forces acting on the water that's occupying the space where we're going to put them. Picture a sphere of water within the volume of water that's in the tub. What are the forces acting on that watery sphere? Well, the force of gravity is pulling it down, and since the sphere is in static equilibrium, there must be some force pushing up on it, counteracting the force of gravity. We call that force the buoyant force, and it comes from the fact that water pressure at the bottom of the sphere is greater than the pressure at the top. Now let's put the billiard ball where the sphere of water used to be. What are the forces acting on that? The force of gravity that's pulling down on the billiard ball is stronger than the force that was pulling down on the sphere of water. That's because the billiard ball is denser than water. So even though the ball and the sphere of water have the same size, the ball is much heavier. But the buoyant force on the billiard ball is exactly the same as it was on the sphere of water, since they're the same size and shape. That's Archimedes' principle. There's a buoyant force pushing upward on objects in water, and it's equal to the weight of the water that the object displaced. The billiard ball weighs more than the sphere of water that it's replacing, so there's a net downward force on the ball, and it sinks to the bottom of the tub. But if you were to fill that sphere of water with a racquetball, the opposite would happen. In that case, the force from gravity pulling it downward is weaker than the force pulling down the sphere of water, but the buoyant force pushing upward is still the same. So there's a net force upward on the racquetball, which is why it floats to the top of the tub. Some of the racquetball will pop out of the water, but some of it will stay underwater. In fact, once it stops moving, the racquetball will displace a volume of water that weighs exactly as much as the ball. Because at that point, the buoyant force pushing the racquetball upward and the force of gravity pulling the racquetball downward have the same magnitude, so they cancel each other out. Thanks to Archimedes, we know why objects float and sink.
Equilibrium of forces. Welcome to this lesson on equilibrium of forces 2. Now we'll be looking at moments of a force. Moment of a force. The moment of a force about a point or as a C is the turning effect of the force about that point. It is equal to the product of the force and the perpendicular distance of its line of action from the point C. As you can see with the image, it is equal to the product of the force and the perpendicular distance. So moment has a formula: force times perpendicular distance. The moment of a force brings about a turning effect. For instance, when we turn on a tap, tighten a knot with a spanner or a screwdriver, or we screw a nail in or out of a wood with a screwdriver, we are exerting a turning force and producing a turning effect about a point or along its axis. So there are certain conditions of equilibrium under the action of parallel coplanar forces. Now, for us to understand this, what are coplanar forces? Coplanar forces are forces that lie in the same plane. parallel forces are forces whose lines of action are all parallel to each other. So when we say parallel coplanar forces, we mean forces that are parallel and in the same plane and whose line of actions are parallel to each other. So the conditions for these forces to be in equilibrium are: 1, the algebraic sum of the forces acting on the body in any given direction must be 0. That is, the sum of the upward forces must equal the sum of the downward forces. We can put it in another way as the sum of the forces acting in one direction must be equal to the sum of the forces acting in opposite directions. Now this is the condition. Then there's another condition: moments. The sum of clockwise moments must equal the sum of anticlockwise moments. Let's look at moment of a couple. The moment of a couple is the product of one of the forces and the perpendicular distance between the lines of action of the two forces. Now consider a wheel of diameter d. If a force P acts tangential to D, then the moment is P times D. Moment is equals to P times 2r, as diameter is r over 2. Now there is a special case. Let's look at the equilibrium under the action of 3 non-parallel forces. Remember your triangle law of forces. The condition here is that the 3 forces must lie in a plane for them to be in equilibrium. Their lines of action must meet or intersect at a point. Thank you. Their lines of action must meet or intersect in a common point. The vectors representing the 3 forces can be arranged to form a closed triangle with sides respectively parallel to the directions and proportional in length to the magnitude of the forces. So remember your triangle law. We are just quoting the triangle law of forces is in another way here. So the principle of moments. If an object is in equilibrium, the sum of the clockwise moments about any point is equal to the sum of the anticlockwise moments about that point. What do we mean? Imagine this seesaw, and then which is pivoted at the middle. Total clockwise moments about a pivot is equal to the total anticlockwise moments about a pivot. Don't forget, moment has a formula: force times perpendicular distance. When a beam is balanced, we say that it is in equilibrium, and by that, if an object is in equilibrium, the force on it must be balanced. No resultant force. The turning effects of the forces on it must also be balanced. No resultant turning effects. So these are some of the conditions for an object to be in equilibrium. So let's look at a worked example. The diagram shows a uniform half-meter rule balanced at its midpoint. A force of 100 Newton is hung at one end, and a mental block of unknown force, or whose force is to be determined, is hung at the opposite end. Both forces are at distance 15 centimeters and 20 centimeters from the pivots, respectively. How do we determine the mental block, the force of the mental block? We use the principle of moments, force times distance, that is, sum of clockwise moments equals the sum of anticlockwise moments. So when we consider the force at the distance about the one point, must balance the force on the distance about the opposite points. So when you do that simple algebra, you will get the force of 75 Newton. Please take note. Now let's look at center of gravity, which is also called center of mass. The center of gravity of a body is the point about which the entire weight or mass of the body seems to act. The center of gravity may be regarded as the point of balance. The center of gravity of a body is in the same position as its center of mass. Please take notes. The center of gravity of a body is in the same position as a center of mass. And one way of determining the center of gravity of a uniform meter rule is to suspend it on a pivot in the laboratory freely in the air and to determine its balance point. That is to say, when the meter rule is no longer waving downwards, is suspended freely, we say it is balanced. And at that point, we can take note of its center of gravity. So, properly, we define the center of gravity as the point through which the line of action of the weight of the body always passes, irrespective of the position of the body. We define the center of gravity as the point through which the line of action of the weight of the body always passes, irrespective of the position of a body. Now, the center of gravity of a regular and uniform material, for instance, a rectangle, is at the center, same as the sphere. They are geometric centers. For a uniform ruler, center of gravity is at the center, and when supported at this point, it balances. When supported at any other point, it topples, that is, it goes down or it begins to wave. The center of gravity of certain object lies outside the actual material of the object. For instance, you have this L shape and the U shape. Cut a letter L out of a metal or plywood and stick on a sheet of thin paper to complete the rectangles as shown. Now you can see that the center of gravity is a bit different from a uniform sphere or a uniform a rectangular block. Now, finding the center of gravity of irregular shape, e.g. a lamina, you perforate it. That is to say, you are provided with irregular lamina, thread and a bulb, nail clamped in a stand. Procedure: make 3 hole perforation A, B and C on the lamina. As you can see, first hang it on the point A. So we hang a thread with plumb line on the thread A so that it can swing freely on a nail clamped in a stand. To locate the vertical line through A, tie a plumb line to the nail as shown above. So you tie the plumb line to the nail as shown, and it's at that point A, the O. When the plumb line comes to rest, draw a line of plumb line by using ruler and pencil. Mark it as line AD as shown. Then repeat the same procedure with point B and C. Where the line AD, BC and CF intersect is the center of gravity of the lamina. So please take notes. It's just a simple experiment. Stability of objects. There are 3 types of equilibrium. We have the stable equilibrium, we have the unstable equilibrium, and we have the neutral equilibrium positions. What do we mean by stable equilibrium? A body is said to be in a stable equilibrium if it tends to return to its original position when displaced. Stability can be increased by lowering the center of gravity. For instance, in a race sports cars, the center of gravity is low and the tire of the car is wide. So a low center of gravity and a wide base helps to increase the stability of a body. So examples of stable equilibrium are a cone resting on its base, a racing car with a low center of gravity and a wide base, a ball or a sphere in the middle of a bowl are all examples of objects in stable equilibrium. Now, which of these glass is more stable? If you look at it, glass D is more stable as it has a lower center of gravity and a wider base. Glass D is the answer. Now, unstable equilibrium. A body is said to be in an unstable equilibrium if when slightly displaced. If when slightly displaced, what happens to it? It tends to move further away. Thank you. It tends to move further away from its original position. So a body is said to be in an unstable equilibrium if when slightly displaced, it tends to move further away from its original position. So please take note. Now, example of an unstable equilibrium. When talking about unstable equilibrium, we have a cone or an egg resting on its pointed end or apex. We have a ball or sphere resting on an inverted bowl. Then, let's look at neutral equilibrium. A body is said to be in neutral equilibrium if when slightly displaced, it tends to come to rest in its new position. A body is said to be in neutral equilibrium if when slightly displaced, it tends to come to rest in its new position. Example, a cone or cylinder or an egg resting on a side, a ball or a sphere on a smooth horizontal table.